Welcome to another session on DC transfer characteristics. In this session, we'll see the pass transistor circuits, the construction of pass transistor, the output voltages, an overview on static CMOS inverter, derivation of DC transfer characteristics, and a quick view on noise margin. The pass transistor is a type of static CMOS. It's a very simple circuit with just one NMOS or a PMOS. We'll see the operation of the pass transistor. Let the drain voltage and the gate voltage be kept at VDD. The source voltage will also rise up and it will try to be equal to VDD, but it can never go beyond VDD minus VT. It's because between the gate and the source, a voltage of VT has to be maintained if the MOSFET should remain on. So the source voltage will be VDD minus VT when the drain voltage is VDD. So a whole VT gets dropped and we say that a pass transistor cannot pass a good one, but it passes a degraded one. Consider the next case when the gate voltage is 0 and the drain voltage is at VDD. Even though the drain voltage is high, the MOSFET cannot conduct because its gate voltage is 0. Consider the third case when the gate voltage is VDD and the drain voltage is 0. Now the MOSFET does not have any problem in maintaining VT between the gate and the third terminal. It passes 0 as such. So when the voltage or when the drain voltage is at VDD, output will be less than VDD, and when the drain voltage is at 0, output will be 0. So we can say that the NMOS pass transistor passes degraded ones and good zeros. Same analysis is done for the PMOS pass transistor. We can conclude that PMOS passes degraded zeros and good ones. On the same line, the analysis can be done for all the four pass transistor circuits. The static CMOS inverter is again a static CMOS. It has a PMOS and an NMOS. The input voltage is given to both the PMOS and the NMOS. The input voltage to the NMOS is Vn minus 0, which is equal to Vn. And the input voltage to the PMOS is Vn minus VDD. Shows the different operating regions of the NMOS. Recollect that the NMOS or the PMOS can exist in two regions. When the input voltage is less than VTN, the MOSFET is said to be cut off, and the NMOS is said to be on when Vin is greater than Vt. When it is on, it can be either in the linear or the saturated region depending on the value of VDS. Table shows the operating region of the PMOS. The operating regions are derived based on the fact that the input voltage to the PMOS is Vin minus VDD. Look at the figure which has been shown at the side. There is a PUN and the PDN. The PUN is the pull-up network and the PDN is the pull-down network. The pull-up network or the PMOS is called so because it pulls the output voltage towards VDD. The PDN or the NMOS is called so because the output voltage is pulled down towards ground by this network. The DC transfer characteristics of the static CMOS has been derived using the drain characteristics of the PMOS and the NMOS. The one in green is the drain characteristics of the NMOS and the characteristics in blue is the characteristics of the PMOS. The IV characteristics of the P device and the N device were shown in the previous slide. In the slide, the IV characteristics of the P device is reflected above the x-axis. The step is followed by taking the absolute values of the P device, VDS, and superimposing the two characteristics. The operation of the CMOS inverter can be divided into 5 regions. The figure shows the DC transfer characteristics of the CMOS inverter. Region A is the region between V input is greater than or equal to 0 and less than VTN. Here, the N device is cut off and the P device is in the linear region. Applying the current equation for cutoff and linear, we obtain that the output voltage Vout is equal to VDD. Region B is characterized by V input is greater than or equal to VTN and less than VDD by 2. Solving the equations as we have done in the beginning of this chapter, we obtain NMOS in saturation and PMOS in linear. The output voltage, as said before, can be obtained by solving the current equations in saturation and linear regions. Region C. Here, both the PMOS and the NMOS are in saturation. It's a well-known fact that when a MOSFET is in saturation, it can be represented as a current source. When two current sources are in series, it is an unstable condition. A small input voltage has a large effect at the output. This makes the output transition very steep, which is shown in figure. The D region is described by V input is greater than VDD by 2 and less than or equal to VDD plus VTP. The P device is in saturation region while the N device is in its non-saturated region. In region E, V input is greater than or equal to VDD minus VTP. The N device is in the linear mode and the P device is in cutoff. Some new terms and some new theory are proposed in this slide. VINV, the threshold voltage, is the gate threshold voltage. It is the voltage at which the gate or the CMOS inverter switches from a high to low. Here, this depends on the ratio of beta n to beta p. What is beta? If you remember, beta is mu Cox into WL by T. If beta n by beta p is decreased, the transition region shifts from left to right. However, the output voltage transition remains sharp. Noise margin is a parameter closely related to the input-output voltage characteristic. This parameter allows us to determine the allowable noise voltage on the input of a gate so that the output will not be affected. The specifications most commonly used to specify noise margins are NML and NMH. NML is the low noise margin and NMH is the high noise margin. These in turn lead to 4 different values. First one is VIH minimum, which is the minimum high input voltage. The second quantity is VIL maximum, which is maximum low input voltage. This term is VOH minimum, which is the minimum high output voltage. Fourth term being VOL maximum, which is maximum low output voltage. This leads us to NML is equal to magnitude of VIL max minus VOL max and NMH is equal to magnitude of VOH minimum minus VIH minimum. Thank you.